Welcome to our Introduction to Time Series. Time series is a quantitative variable measured at regular intervals. For instance, quarterly earnings for Ron John's Surf Shop, annual sales at Amazon.com, number of hits at Canvas.instructure.com every hour. So any data that you have that's measured at regular time intervals, that's quantitative, is a time series. We have historic data from past time periods, and we may be interested in building models to forecast values for future time periods. We can use the time variable itself as a predictor, or we can use the past history of the series to make predictions. Time series data, again, we talked about this in the beginning of the semester, are plotted as a line graph with time on the horizontal axis. The following notation is used. Y sub t is the value of the time series in period t, and t is an index denoting the time period, 1, 2, all the way through n. And then, of course, y sub 1 through y sub n is the data set for analysis. So we've got two pictures of time series data. The one on the left has two different scales on it. One's on the left side of the picture and one's on the right side. Again, I don't recommend doing that. It's hard not to distort data when you do this, but you'll see it quite often. And then the picture on the right just has one quantitative variable with three categories. So it broke it out into three separate lines. Notice in each of them you could extract some sort of a trend out of the data. And then there's also other variation. On the left picture, looks like there's some seasonal variation. It looks very regular to me. And then some also unexplained. And then on the right, there looks like there's a lot of unexplained variation and maybe some seasonal variation too. We'll be talking about these. But first, another term. Periodicity is the time interval over which your data are collected. Data can be collected once every decade, year, quarter, month, week, day, hour. You get the picture. So we're going to talk about four components of time series: trend, cycle, seasonal, and irregular. These components are assumed to follow an additive or a multiplicative model. The additive models for data of similar magnitude, short-run or trend-free data with constant absolute growth or decline, and the multiplicative generally for increasing or decreasing magnitude, long-run or trended data with constant % growth or decline. Notice that the multiplicative model becomes additive if logarithms are taken for non-negative data. All right, so we've got our four components that we want to talk about. So the first one is trend, and that's the general movement over all the years. Trends can be steady and predictable, increasing, decreasing, or staying the same. A mathematical trend can be fitted to any data but may or may not be useful for predictions. So of course the trend pictured here in the example is linear, but we could fit a quadratic, we can fit a cubic, we can fit all sorts of different types of models to explain the overall pattern, the trend of a series. All right, so now let's talk about cycle. This is a repetitive up and down movement about a trend that covers several years. Now this is the one that's probably talked about the least because over a small number of time periods, cycles are undetectable or may resemble a trend. Now one that you will commonly hear about is the seasonal component. This is a repetitive cyclical pattern within a year or within a week, day, or other time period. Think about gasoline prices. They tend to rise in the summer, in the warmer weather when people are traveling, and go back down in the colder months. So there's a seasonal component to gasoline prices and to many other types of data. So by definition, annual data have no seasonality. All right, so irregular part of the pattern is your residuals, just like we had in regression. So this is also called the random error component or random noise, reflecting all factors other than trend, cycle, and seasonality. It's the unexplained variation that's always going to be there. Short-run forecasts are an option if your data are mostly irregular. So there are two main types of time series models. The causal models we're not going to get to. They're beyond the scope of this course. And then in the plain regular time series models, there's trend, decomposition, smoothing, and the autoregressive integrated moving average models. We're going to talk about trend. We're going to talk a little bit about decomposition and a little bit about smoothing. So that's what you're going to get in this module. All right, so let's talk about trend models first. We've got the linear model, which you're already familiar with because we've fitted simple linear regression. We've got the exponential model. it also has two parameters like the linear model, and it's useful for growth rates. You can see the picture on the right side over there. It's y sub t equals a times e, that's a special number in math, to the b times t power. And then we've got the quadratic. So this is three parameters, and it's useful when data has an inflection point. So you've got your intercept a plus your b, that's your coefficient for your time variable, plus your c, which is your coefficient for your squared time variable. All right, so let's have an example. Let's call in and graph data on quarterly flooring sales. As you can see from the picture of the data on the right, we've got quarterly sales from 2006 through 2011, so 24 observations. So I called in my data set, I attached it, and then I plotted the sales, but I put another argument in my plot call, type equals L. That means connect the dots with a line. And so we've got a nice line plot of our data. And we see that it looks like there's a trend there. So let's try to fit the linear trend first. So what I do is I created an index variable. In time series data, you can, sometimes your dates don't have they're not easily translatable to be the predictor in a model. And so it's very, very common, instead of putting in like years, to create an index variable. So we had 24 data points. So I created this variable that was a vector that concatenated the numbers 1 through 24. All right, so I'm going to call this linear fit, and I regressed the LM sales on index, because sales is what I'm trying to predict, that's my y, and the index variable is my time variable. And I added the fitted model by using the ab line call in R. And you can see it pictured here. And it looks okay. It certainly doesn't capture the whole, all the variability. Let's see how well it did in terms of R squared. If we look at the output, we can see that the R squared is about 63%. So not super great, but it is a start. So now let's talk about fitting the exponential model as the trend. And this is what we would do in practice. We might try a couple models and see which one fits better. So let's try the exponential. So that's the model's y sub t equals a times e to the bt. That's going to be our fitted model. And to fit the exponential model in R, we're going to fit the natural logarithm of the y against the x predictors. Note that log of y in R is the ln function. That does the natural log. There's a separate log function for base 10 in R. All right, the intercept from this needs to be transformed back using a equals e to whatever the intercept is from the output. So let's take a look at this one. I called this one exp fit, and that's the lm function again, but instead of just putting sales as my y, I did log sales as my y. That's the natural log of sales on the index. And then to fit my line onto the picture, the AB line doesn't work here. So I just created a T sequence from 1 to 24 by 0.01. And then I actually took the output from fitting the model here. Notice the intercept's 5.302354 and the index is, the time variable is 0.038917. I just actually calculated out what the predicted value would be for each value of that T sequence by taking e to my intercept and then e to the b times t. And then I used the lines call to plot the t against the exp that we just calculated. And anyway, you can see the picture right here. It looks like it fits a little bit better than the linear model. The R squared is up just a teeny tiny bit at 64%. Okay, so let's try the quadratic model. This one looks better to me just by glancing at it. Here we do the same game that we did in multiple regression. We've got to square that index predictor. So I create a variable before I do my fitted model. I call it index 2, and that's the index vector squared. And then my quadratic fit is LM of sales on index plus index squared. And again, I plot my sales type equals L. And again, I create a sequence from 1 to 24 by 0.01. I calculate the value of the fitted model for each value in that sequence. And those numbers are from the output that you can see on your lecture notes. And I did the lines again, lines x comma y. And the picture's here, and it looks like it fits a little better. The r squared went up just a tiny bit. It's almost 65% now. And we have our output. All right, so we've got these three competing models. None of them are super great. There's a lot of unexplained variability, about 35% or more for each one of these fitted trend models. So obviously trend is not capturing all of the variability in the data. Let's talk about collinearity. So notice that the quadratic model, the t and the t squared, are completely related. Just like in multiple regression, since they're related, your VIFs are going to be very, very high. These VIFs are 17. So if the variance inflation is a concern, then you can center the squared term just like we did in multiple regression. You can use t minus the mean of the t's squared in place of t squared. All right, so I did that here. I took my index minus the mean of the index and squared it first and then put it into my quadratic fit. I called it quadratic fit center. And you get your coefficients. The multiple r squared is still the same as the original quadratic fit, about 65%, and it fixes your variance inflation problem. Okay, so the trend models only explained about 65% or less of the variability in sales. So we want to take into consideration other components. So it looked like there might be a seasonal component here. So let's go ahead and try to take into account the seasonal component. So to account for, one way to account for the seasonal component is to add a term to the model. So let's fit the linear trend to the flooring sales data and add a term for the seasonal component quarter. So notice that I called it seasonal means fit. I regressed sales on index, my time variable, and I added another term. I added quarter. Now if you'll look at your data on the snapshot of your data on your lecture notes, you'll see that quarter is recorded as a number. So in R, since that's really a categorical variable, since it's recorded as a number, we have to tell R that it's a categorical variable by using the factor function on it. So here's the output, and we can see that the R squared went all the way up to 90%. This is a very big improvement over just our trend model that we fitted before. So obviously, taking into account the seasonality is helping account for a large portion of the variability in these data. So what did we do when we fitted this model? We actually took the original sales data and we broke it into its linear component, its seasonal component, and, of course, the irregular part, the residuals. So I've graphed those for you so you could get a visual image of what we have done by adding the linear term to the model and the seasonal term. And you know the errors are always there. All right. Now, one thing that I want you to notice is, we talked about it, but we fitted our model with index as our linear portion predictor, but we could have used year as our predictor in our case. So let me show you what happens when you do that. Let's fit the model with year and compare the predicted value for the first quarter in 2012. So I refit the same model that we just did with year instead of index, and we get our estimates. They're a little bit different than they were before, but that's okay. That's because you're going to plug in a different type of number into your model when you're making predictions. So if I wanted to make a prediction on the first quarter, then I would use my intercept, negative 115,008.017857, plus the coefficient on year, 57.46286, times the actual year itself, because I fed the model the year when I made the predictions. And I get 610.125575. Now if I look at the same model that we were working with before, where I used index as my predictor instead of year, my coefficients have changed, my estimates have changed, but that's okay. It's just adjusted because you're going to feed it different kinds of data. If I want to predict the first quarter of 2012, that's going to have an index of 25. So here, I take my intercept and add to it the coefficient of index, 14.366071, times the index of 25, and I get 610.124989, And this slight difference is just due to round-off error, which is more pronounced when you're putting in a big number like a year. All right, so now let's go back to practicing using our model to make predictions. So let's use the model to predict sales for the second quarter of 2012. All right, so I've got my model, 250.973. I need to figure out what to put in for index. Well, if you're looking at your data on your lecture notes, you'll see that the last index was 24, and that was for the last quarter of 2011. So that means the second quarter of 2012 would have an index of 26. And if I want to predict for the second quarter, I'm going to plug a 1 in for quarter 2 and a 0 in for quarters 3 and quarters 4. And when we plug those numbers in, we get $547.62. Now you can hand calculate your predictions, or you can use the predict function in R. So what you're going to do is you're going to tell it that my data for prediction, you're going to make it into a data frame, data.frame, of the index equaling 26 and the quarter equaling 2. Notice that the index equaling 26 is not in quotes and quarter is in quotes, and that's because quarter is a categorical variable. Then you use the predict function based on your fitted model. Seasonal means fit is what we called ours, comma, the new data for prediction, and you get the same number out, basically, that we did when computing it by hand. All right, let's practice making a prediction for the first quarter of 2012. All right, so what do we put in? Our index is going to be 25, since the last quarter of 2011 was the index 24. The first quarter of 2012 is going to be an index of 25. And then for the first quarter, since we don't have a term there for it, we're just going to plug in 0 for quarter 2, 0 for quarter 3, and 0 for quarter 4. And that's going to give us our baseline value of quarter 1. And we get $610.12. Or we can use the predict function in R. This time our new data frame is going to be index equals 25, quarter equals 1 in quotes. And again, we're predicting on the seasonal means fit model with the new data that we just gave it, and it gives us basically the same estimate. The difference is only due to round-off error. All right, but now we're thinking like statisticians, and we know that we want to buffer how far off those one number best guesses for our forecasts are. We've already studied confidence intervals for the mean response and prediction intervals in the regression setting. We're going to use these same ideas in this time series section, except that we're almost always interested in a prediction interval since we're looking to capture a specific value at a future point in time. So we often refer to these prediction intervals when we're talking about time series as forecast intervals. So let's find a forecast interval for sales in quarter 1 in 2012. Well, we can use the predict function again by feeding it the 25 for the index and the quarter equal to 1 in quotes, since that's a categorical variable. And when we call the predict call, we're going to add another argument in the function, interval equals prediction. And that's going to give us a confidence interval, a prediction interval, our forecast interval. So notice that the estimate of sales is 610.125, and then we give a range of values for where we think that might actually end up being, between 509.196 and 711.054. So that's the way you can get a prediction interval, a forecast interval. Also, the same things apply that carry over from regression. The farther in the future you try to make a prediction, the wider your forecast interval is going to be. Okay, so now we're going to talk about smoothing. So you can use smoothing when the time series is described primarily by unsystematic patterns. So if it just looks like random noise, you could try smoothing it. The simple moving average is one way to smooth a series. You're going to compute the average of the m most recent observations, and it's called a moving average because for a new observation, the average is updated using the newest, most recent observation and dropping the oldest. So the simple moving average is just the sum of the m most recent observations divided by m. So we've got an example. According to the Energy Information Administration, the United States consumes about 21 million barrels, 882 million gallons of petroleum each day. About half of this consumption is in the form of gasoline. The file gasprod.csv contains weekly U.S. finished gasoline production in thousands of barrels per day. Notice here that we have our date column. We've got a week column, which we could use instead of creating a separate index. And then we've got our response variable, production. So we're going to construct a 3-period moving average. We're going to plot the production against the moving average, and then we're going to use the moving average series to forecast gasoline production on May the 29th of 2009, which would be week 22. Okay, so I called in the file, I attached it, and I plotted the production with type equals L so we could see just how irregular this series is. No obvious trend, lots of random noise, it looks like. All right, so we're going to install a package called TTR and then load it using the library TTR call. It has a function in there for the simple moving average called SMA. So I did SMA on the production column with my number, my M, equal to 3. It takes N equal to 3 in the function. And then I plotted the production with type equals L, and I made it red. And then I used my lines call to plot week against the moving average based on the 3-period moving average. And I gave it a dotted line by using the line type equals 2 argument and colored it blue. And then you can see how I added a legend on there. The 15 and the 9300 are just the X and Y coordinates for where I wanted the legend to start. And then I told it what to put in the legend. So there we've plotted our series against our smoothed series. Now, when I look at the actual values for the smooth series, I can do that by column binding week and my smooth series, MA3. I called it MA3 when I created it in R. Notice that the first 2 entries of the moving average calculated by R are NAs. The third entry, 8885.666667, is the average of weeks 1 through 3. So that number is going to be our forecast for time point 4. So now, what is the forecast gasoline production on May the 29th, 2009, which is week 22? Well, we see that for week 21, the smooth value is 8941. And that's the average of weeks 21, 20, and 19. So that number is going to be our predicted value for week 22, 8,941,000 barrels. Okay. The moving average is popular because of its simplicity, but has shortcomings. The choice of M is arbitrary. You can play around with it and see which one fits the best. And it also gives equal weight to all recent M observations, and this may not always be appropriate. So exponential smoothing assigns exponentially decreasing weights as the observations get older. This is similar to the simple moving average, that the exponential smoother continually revises the forecast in light of more recent observations. So we're going to let A sub t denote the estimated level of the series at time t, where it's defined as alpha times y sub t plus alpha times 1 minus alpha times y sub t minus 1 plus alpha times 1 minus alpha squared times y sub t minus 2. That's the next one down in your furthest away in your list of values in your time series, etc. And alpha is between 0 and 1. A higher alpha indicates a higher speed of decline. It can be shown that A sub t actually collapses to be alpha of y sub t plus 1 minus alpha times the most recent A sub t minus 1. And then forecasts are made as your predicted value for t plus 1 is A sub t. Okay, so we're going to use the gas production data to produce the exponentially smooth series with alpha equal to 0.2 and A1 equal to Y1. We're going to plot the production against the smooth series and then use it to make a forecast again for week 22. All right, so again in the TTR library, in that package, there's a function for exponential smoothing called EMA. So I guess it's exponential moving average is what it stands for. And I did that on the production column with n equal to 1 to start it at A1 and the ratio equaling 0.2. And then I plotted it again, type equals L, I colored it red, used the lines function to plot week against the exponentially smooth series, gave it a dotted line, line type equals 2, color equals blue, and again I put a legend on it. And you can see that this one's a little bit smoother than the simple moving average. okay? And we can use it to make a forecast. So again, remember that your predicted values for the exponential smoother for t plus 1 time point is just to use a sub t. So if we want to predict for week 22, we're going to use week 21's exponentially smoothed value, 8933.289426. So we're going to estimate that for week 22, May 29, 2009, about 8,933.29 thousand barrels. Okay, so some final notes. The centered moving average is a tool for smoothing when attempting to seasonally adjust data. The centered moving average gets a little bit more tricky, just has some other things to take into consideration, especially when you have an even number in your period that you want to average over. And it takes the average of half the observations are below the current and half are above it. So it's a centered moving average. When you apply a moving average, you essentially get rid of the seasonal component. And so to extract the seasonal component, you would have to calculate seasonal ratios to extract that seasonal component. So we didn't get to that centered moving average and extracting the seasonal component, but you did learn a lot. And just keep in mind there are lots of other options for time series which are just beyond the scope of this course.